Hello and welcome. In today's lecture, we will see the topic of activation function. So let's start. But before going to explain the activation function, let me summarize the neuron. If you remember from the neuron lecture, from the McCulloch-Pates or from the perceptron lecture, we discussed that in a neuron, first of all, a weighted sum of its inputs is calculated and then a thresholding function is applied to decide what output is to be produced. So if there are inputs such as x1, x2 up till xn, okay, in the neuron, the first function g was responsible for calculating the weighted sum, and the second function f was then applying some threshold to decide what has to be produced at the output. Okay, if these are the inputs, the x1, x2 up till xn, with these inputs there are associated weight values is w1, w2 till wn also exist. The first function g calculates the weighted summation as wi multiplied by xi, where the I starts from 1 till n plus b, the bias, which is some constant value. The second function f was then applying thresholding logic to this calculated weighted summation. If this weighted summation is greater or equal to some threshold theta, then the neuron will be activated and will output a value is 1, and otherwise it will output a value is 0. Okay, so this was the thing that we have discussed in our neuron or in perceptron lecture, and we mentioned that a neuron is activated when the weighted summation of the inputs crosses a threshold. Okay, so let's assume if you have set a threshold theta to 0.70. In this case, your neuron will be activated when the weighted summation wi xi plus b, where I starts from 1 till n, will be greater than or equal to this threshold, which is 0.70, and otherwise it will output a value of 0, mean it will not be activated. So now if you have the threshold set to 0.70, then if your weighted summation has a value is 0.69 and 0.71, then in this case your neuron will provide significant different results. Because the one value 0.69 is less than, it is below the threshold, and the another value 0.71 is above the threshold theta. Even these two values are very close to one another, but the threshold is set to 0.70. That's why at the output different results are obtained. So the thresholding function is basically a kind of step function, okay, which indicates that a sudden change in outputs can occur even with a small change in input. The step function is looking something like this. Okay, so this is 0 and this is 1. This is your output y, and on this axis there is your weighted summation values such as the wi xi plus b, I starting from 1 till n. So this is your threshold. Let's this is 0.70. So when you have a value of the weighted summation equal to 0.70 or above it, then your neuron will be activated. It will output a value is 1, whereas otherwise it will output a value is 0. Even if the calculated weighted summation value is very close, such as if there are a value is 0.6999999, still you will get the output value of 0 because again this value is below than the threshold. And this is not a problem characteristic, but it's a feature of the neuron function that acts similar to a step function. But in a real world situations, this behavior is not occur because in a real world situations, usually a smoother decision functions is used. So that's why the activation functions were introduced because it is something like a kind of smoother decision function. An activation function is basically a mathematical function that is applied to the output of a neuron, and it determines whether the neuron will be activated or not, and if it will be activated, then how much it will be activated. And the another thing with the activation function is that the activation function introduces nonlinearity to the neural network, which allows the neural network to learn the complex relationships. So now with the activation function, the general neuron would become something like this. A is equal to f of z. So before considering this or before understanding this, let's assume that you have the input is x, associated weight is w, the associated bias, which is some constant value, is b. Then from this, first of all, a weighted summation will be calculated as w x plus b when there will be one input, when there will be several starting from I is equal to 1 up till n, then the weighted summation will be calculated as wi multiplied by xi plus b, the bias. So this weighted summation is equal to the z, this z, okay, which will be the input to the activation function. And then to this calculated weighted summation, the activation function if is applied, and then it generates the value a, the output, which is the neuron output. And that value tells whether the neuron is now activated or not. And if it is activated, then up to which extent it is activated. Okay. Visually, it will now look something like this. First of all, there will be inputs such as x1, x2 up till xn. Then from these inputs first, then a weighted summation will be calculated as wi xi plus b, where I will be starting from 1 up till n. And then next to this calculated weighted summation, the activation function f will be applied. Okay. So to this calculated weighted summation, when the activation function f will be applied, then the output will be generated. So now the output will not be only 0 and 1, but it will be something value in between them or above the 1 or below the 0, depending on the type of activation function that you have used. So this was the concept of activation function. As we have mentioned that the activation function introduces nonlinearity to the neural network. So now the question is why it is important to introduce the nonlinearity to the neural network. Let's suppose if you have a neural network something like this, where you have with first the input layer, then the two linear layers, and then the output layer. In this case, even if in the neural network there are several layers, but the output is still linear. Okay, mathematically, the output is looking something like that: W2 multiplied by W1 with x plus B1 plus B2, where W1 is the associated weight with the first layer, with this layer, with the linear layer 1. X is the input, B1 is the associated bias with the first layer. The W2 is the weight associated with the second layer, this layer, and B2 is the bias associated with this second layer. Therefore, the network can't learn highly complex patterns or features such as the image features or speech patterns or nonlinear decision boundaries and so on and so forth, because the output is just a linear combination of the input passing through these several layers. Okay, and in real world there are non-linear feature exist, like one could be related with the another one. It's not possible always that the all the inputs will be related linearly with one another. There exist some non-linear decision boundaries. So when you have such type of neural network, like without the activation function, then it's not possible for a neural network that it will learn the non-linear decision boundaries or non-linear features. But when but with the activation functions, this problem is solved because the activation function replaces the threshold functions, which acts a kind of step function, something like this, with more smoother activation function. So if the step function is like this, let me clear this. Uh, this is a step function. With the activation function, okay, the threshold function like this, that x is a step function, they are replaced with more smoother activation functions, something like this. Okay, or linear functions, something like this, or they are basically replaced. We will see them in the future lectures. There are several different activation functions available, but the most popular ones are the step function, sigmoid function, 10H, ReLU, leaky ReLU, and the softmax, so on and so forth. This was all about today's lecture. In our next lecture, we will explore and we will discuss all of these activation functions, these 6 activation functions in more detail. I hope you will have enjoyed today's lecture. If you like today's lecture, like it, share with your friends, and subscribe the channel. Thank you so much. See you in the next lecture.